Perfect, perfect, perfect,
Hi guys, welcome to this lesson, Introduction to Electronics Basics. So we're going to be looking at electricity and we'll also be looking at circuits, and at the end of this lesson I'll also build something practical that you can see what electronics is all about. So let's get started. So what is electricity? Electricity is just another form of energy transferred through a flow of charge. So I'm not going to get into the physics of it and the electronics and the atoms, but for now just look at electricity. It's just a form of energy. So just like you have energy to jump up and down, and you have energy to do anything, so electricity is just another form of energy. So that's how I want you to look at it right now. So electricity is another form of energy transferred through a flow of charge, and we're going to describe in a minute what a flow of charge it means. So view electricity as energy, So there's different sources of energy. It can be solar, come from the sun, it could be wind, it could also be a power station like Eskom, so it could also be a battery. So that's where we get energy or electrical energy. Those are all the sources. Okay, not all of them, but those are some of the sources of electrical energy. So you can get electricity anywhere. So now I'm going to describe the concept of flow of charge, right? We said electricity is transferred through a flow of charge. So we're going to look at a basic circuit here. So what we have here is a voltage source, and we have a resistor, and we have conducting wires this side and this side. The first concept we're going to learn about is voltage. So voltage is basically the potential energy stored in that electrical source. For this example, we are looking at a DC circuit. So the voltage would be the measure of the energy, electrical energy that is here. And electricity always flows from the highest potential energy to the lowest potential energy. And it is converted into many forms like heat or kinetic energy if you're using a motor. So the electricity is converted into many other energies. Sometimes it's lost through heat. So right now what I want you to get is that V is used to represent voltage, which is the energy capacity of this circuit, right? Voltage, it's what it's called. That is the energy of the electricity. The next thing we're going to consider is current. So current is simply the flow of charge. Now we said electricity is transferred through the flow of charge. So until the charge flows, we don't have electricity circulating, right? So electricity needs to move from the battery of your phone all the way up into the circuit of your phone and all the nitty-gritties that are there. So as illustrated here, we have I, which represent current. That is the symbol for current, and it's measured in amperes. So the A here represents amperes. So current follows the direction of the energy. So we have energy here. We mentioned that we have a voltage source. So it always flows from the highest potential energy to the lowest potential energy. So current will flow in this direction from the highest to the lowest. This could also be ground, right? So we have a voltage source, it's positive this side, and we have negative. What you need to know is that current of the flow of charge flows from positive to negative, or from the highest potential energy to the lowest potential energy. The next quantity we're going to study is resistance. Now, what is resistance? Now, as the name suggests, resistance simply means the resistance of flow. So while current is trying to flow in this direction, you have some resistance here, right? It's trying to reduce the current that flows here, right? And it actually does, depending on the resistance that you have. Another thing that I want you to note is that wires themselves are a form of resistance. So this conducting wires that you see here is another form of resistance. So you have resistance here, which is measured in ohms. We're going to get into Ohm's law in a minute. So what you need to know now is that there's voltage, which is given by this voltage source. It could be a battery, could be anything. But since we're considering a DC circuit, let's just assume it's a battery. So current will flow in this direction, and then it will encounter some resistance. It will also encounter some resistance here. So what will happen when there's resistance? What will happen is that the current will actually decrease. So if you had 10 amperes, if you add resistance, that 10 amperes will be reduced to maybe 5 or 2 amperes depending on the resistance that you have and the voltage source here. I'll show you the relationship between resistance, voltage, and current in just a few minutes. So going back to electricity, we said electricity is a form of energy transferred through a flow of charge. Now, there's two ways that transfer can happen, or there's two electrical signals we can have. We have alternating current and we have direct current. So let us look at the first one, which is alternating current. Alternating current has the shape of this form. So what that means is that you have a continuous signal that is going back and forth. So it goes positives, it goes negative. It goes positive, it goes negative, right? Now, when would we have alternating current? If you want to transfer electricity over a long distance, the best form of transferring it is through alternating current. So rather than having constant current, it is not very efficient. One of the reasons why we use alternating current to transfer electricity over a long distance is because it can be stepped down and can be stepped up as well using transformers, right? But that's a lesson for another day. So that's one of the advantages of using AC over long distances. It's because it can be stepped down and it can be stepped up. So for example, at home, you use 220 volts. That is what is coming out of the wall socket, right? But that is not actually what Eskom distributes. Maybe they might distribute 2000 or 4000 volts or whatever, but it gets to a small unit like called a transformer, and it can step it down quite easily without losing much power, right? So the efficiency using alternating current is much better than using direct current, right? So when is alternating current usually used? Most appliances, so you have your TV, your fridge, your microwave, anything that you basically plug on the wall socket uses alternating current, right? So those are the uses for alternating current, and as I mentioned, alternating current is usually used to transfer electricity over long distances. So now let's have a look at DC current. DC current is also called direct current. Now, as you can see, this graph is pretty quite simple. It's very constant. So it's constant current, constant voltage over a period of time. So it's very constant. So when do we use direct current? So we use direct current over low voltage applications. As I mentioned, your phone, right? So it requires low voltage. So that's why we use DC. That's primarily, for low applications, applications such as a torch, right? It's low voltage, a phone, a camera, low voltage. So we use DC current. So those are the basic two means in which electricity is transferred from one point to the other. Remember, we said it's transferred from an energy source, which could be a battery, a power station, solar energy, into another device. All right, so now that we know what electricity is, we need a way to control it to perform specific tasks like lighting on a TV, a computer, washing machine. We want to push a button and something must happen. So we do this by designing something called a circuit. A circuit is simply a connection of electronic components that allow current to flow in a closed path, and they are connected using conductors. Exactly what we have here. It's components. So this is an electrical component. This is an electrical component. This is called a resistor. And this is the symbol of a resistor. So this is the symbol of a voltage source. It has plus and negative. And these are called conductors, right? And it needs to be closed. If it's not closed, then it's not a circuit, right? And sometimes we can add ground if the circuit becomes a little bit more complicated. But for all practical purposes, this is also a circuit. So it needs to be a closed loop, right? So it starts here and it ends here. So now we have a circuit and we know what a circuit is. Now, what is the relationship between current, resistance, and voltage? For that, we need to turn to our old friend, German physicist Ohm. All right, it's called Ohm's Law. So what Ohm's Law, or what Ohm discovered, is that for any given DC circuit, which is a circuit that is like this, has direct current. So for any given DC circuit, the amount of current that flows through a conductor, which is wires, is directly proportional to the voltage applied across it, and inversely proportional to the resistance at a constant temperature. So what it means algebraically, it means that voltage is equals to current multiplied by resistance, right? You can also use this rule of thumb, or this chart that makes it easy for you to remember this equation. You have voltage here, and you have current, and you have resistance. Remember, this is the symbol for current and for resistance and voltage, right? So that's what Ohm's law said. Ohm's law just discovers the relationship between, so if you have voltage and you have resistance, you can calculate current. If you have current and voltage, you can calculate resistance. So this is how we use the chart. So if you require voltage, remember voltage is on top, we just close this down and we say I multiplied by R, we get voltage, right? Amperes multiplied by ohms will give you voltage. Now, if we want current, we simply close off the current tab, and then we have V divided by R. You can see this is almost like a division sign. This is almost like a multiplication sign. So if we want to calculate the current flowing, we need to divide the voltage with the resistance. And if we want the resistance, we simply say voltage divided by current. So that is the basic relationship between those three quantities. Next up, we're going to look at an actual example. We're going to have an energy source, or a voltage source here, and then we have a resistor, and we have an LED, and we have ground. Now, here's the problem that I want you to solve. You have 9 voltage, right? You have 9 volts, and you have current, which is 20 amperes. So where do we get that from? So you will find as you continue with electronics and designing electronic circuits that there are some components which are standard, and you don't have much choice and flexibility when it comes to that. For instance, a voltage source, like a battery, it comes in 9 volts or 4.5 volts. It's really difficult to find a battery that is rated 2.3 or 2.35 volt, right? Because then there's just infinite possibilities. So manufacturers try to stick to standard like 9 volts, 12 volt, 6 volt batteries, right? So in this particular problem, we have a 9 volt battery, right? And then we have an LED. Now, the maximum rating on an LED most of the time is like 20 milliamperes, right? So you are limited to the LED. You just bought it, and that's how it is. You can't get it to change anyway. But now you want to complete this circuit. Now, another thing I need to mention is that if you're building a circuit, there will be resistance here, but the resistance, if it is too small, it will allow a higher current. The reason why the LED is rated at 20 milliamperes, it means that if it receives current that is more than that, it is going to blow up. And that you don't want that, right? You don't want the light at your house, when you switch on the electricity, it blows up, right? You want to supply the right amount of current to the electrical components. And in order not to supply too much current, we use something called a resistor, which I've already introduced you to it. So a resistor limits the amount of current that flows through the circuit. Now the problem is, how much resistance should we have on the circuit in order not to blow up the LED? So we have 9 volt battery, and we have a limit of 20 milliamperes, all right? So the question is, how much resistance should we add to our circuit so that our LED doesn't blow up? So we need to reduce the current that flows through the circuit. So we know that in order to calculate resistance, we're going to use voltage divided by current, right? Based on Ohm's law. So we know the voltage is 9 volts. We know the amperes is 20. So we can simply say 9 divided by 0.02. 20 milliamperes is 0.02. And that will give us 450 ohms. So what that means is that the resistance that we need in order to power this circuit and to get this LED to turn up is 450 ohms. All right. Now you go back to your components that you have at home or at the store, or the storeman. You want to buy electrical components, a resistor, you've calculated, you need 450, and the guy looks at you and says, you know what, I don't have a 450 resistor. However, I do have a 550 resistor. What you actually need is the minimum, right? So the 450 is the minimum you can use in order not to blow up the current. So if you use 550, it's actually much better, right? You are slightly limiting the current more, but it's better to limit the current than to actually allow the current more than 20 milliamperes, which will blow up. So 20 milliamperes is the limit. You can't go more than that. If you use a resistance that is 400, right, it will exceed that 20 milliamperes. So that is the worst case scenario. So if you use a resistance above 450, it'll still work, like 600 or 800, right, depending on how bright you want your LED. So that's another thing, right? So if you pass exactly 20 milliamperes into this LED, the LED will be very, very bright. But if you pass on slightly less current, the LED will be less. All right, so now we have 9 volts here, and we have 550 resistance, and we have our LED, and we have ground. So now I'm going to show you the circuit in real life and how I built it. All right, guys, so now we have the 9-volt battery. All right, and then we have a resistor here. This resistor is a 560 resistance. Remember what I said, that you need a resistance that is more than 450. And then you have an LED here. All right, now the LED, as we'll discuss in future lessons, it has a positive and a negative. I'm not going to go into detail right now. So all I need to do is to plug it into my breadboard. It's actually challenging to hold the camera and do this. But anyhow, so I'm connecting the resistor now. All right, I'm going to connect it here. It's very challenging. Okay, looks like we got it. All right, so we have the resistor there. Then now I'm gonna connect the negative part of the battery, which is represented by the black cable here. I'm gonna connect it here. Sorry about that. So I'm gonna connect it here. Then I need to take this one and connect it here. All right, guys, with a bit of effort, I was able to add that in. So what we have now is we have the power. Here's the LED, it's lighting up. So we have our current flowing from the red one to the resistor, from the resistor all the way up to the black one, and it goes to the negative part of the battery. So that is similar to the circuit that we design, in that the only difference is that this uses a 560 resistor and the one we designed for is a 550. So that's it, guys. That is a circuit. Thank you for watching, and please don't forget to subscribe. If you have any questions or comments, please drop them in on the comment section. Thank you.
Perfect. Perfect.